/OOP CPP, single word, no spaces, all lowercase. You can follow it on your phone, you can just swipe for the next slide. И я немножко по-русски говорю, только не слишком хорошо. So we'll continue in English. I come from Bulgaria, and anyone here know that? Did anyone know where Bulgaria was before seeing this slide? Okay. Anyone been to Bulgaria? Okay. Don't remember? It's just right next door. So I'm mostly a C++ programmer, but I do other languages too. And for example, this one over here, and if you haven't heard about NIM, check it out, definitely. I'm mostly a game programmer. Most of my career has been in game programming. And I recently started working in a medical software company. I do a lot of open source. You can follow me on GitHub over there, or not follow me, I don't know. You decide. So let's start this topic from afar, in a way. We'll talk about some motivation for our talk. And the motivation is business logic. To put it formally, business logic is a part of a program which deals with the real-world rules that determine how data is obtained, stored, and processed. And this is a mouthful, and it's pretty hard to comprehend, so I'll put it simply. Business logic is the part of the software which deals with the software's purpose. For example, we have this program. The purpose of this program is to add two integers. That's the business logic. So that's the business logic over there. And if you had, say, a Java programmer write the same program, he might do something like this, like overcomplicated stuff, you know. But still, the business logic is over there. It's the same business logic, adding two integers. And there are parts of the program which are not business logic. They can be I/O, presentation, they can be optimizations. But the important thing here is that software is basically split into a business logic part and a not business logic part. And certain pieces of software are pretty complex. But a complex piece of software doesn't necessarily mean complex business logic. For example, this is a ray tracer. This is a ray traced image produced by a ray tracer program. The business logic behind the ray tracer is, I'd say, pretty simple. For each pixel, you cast a ray to the scene, then you reflect or refract it appropriately until you reach a light source. Then you trace the information back to the pixel and determine what the color this pixel should be. Simple, right? But indeed, if you had a budget of 2 hours, a performance budget of 2 hours to produce this image, your program had 2 hours to produce this image from a given input, I say that most of you, if not every single one of you, would be able, on his own, to write this program in, I don't know, days, maybe a couple of weeks, but it's absolutely feasible for a single person to write a program which produces this based on a given input. The complexity in ray tracers is in performance optimizations. So they're pretty complex, but the complexity doesn't lie in the business logic. And do you know what this is? This is Facebook. And I can tell you this. If I give you a budget, now a Facebook page renders for, I don't know, less than a second. If I give you a budget to produce the same information from your software of 2 hours, say you start your software, you produce this information for 2 hours, it will take you, I don't know, years probably to create this program because it has complex business logic. It does have presentation and optimization, of course, but the complexity of the business logic of Facebook is enormous. Do you know what this is? Civilization, yeah? Do you know which number? 6, yeah, Civilization 6. Any Civ fans here? So yeah, certain games, though not all games, do feature very complex business logic. Like Civilization is an example. Most strategies and RPGs feature really complex business logic. And again, if it was up to a single person to write the business logic behind it, it will take them a significant amount of time. Performance side. Do you know what this is? It's Blender. Blender, like many CAD systems, does feature a lot of complex objects, complex business logic, complex interactions between different parts of the software. And do you know what this is? It's Microsoft Project, best software in the universe. Again, Microsoft Project is an enterprise software, and many enterprise software have really complex business logic. But what do we have here? Websites like Facebook are typically written in JavaScript, and JavaScript in the backend too, JavaScript in the front end certainly, but the backend is also a popular place for C# and Java and Ruby and many other languages. In games, yeah, we do have an engine written in C++, but in many cases, the actual business logic, the gameplay logic, what we call it, is written in another language. Lua is especially popular, but C# and Python are also, and there are a whole slew of specifically designed languages to write gameplay logic in. In CAD systems, now Blender is written mostly in Python, but there are CAD systems written in C# too. But for example, the most popular ones, Maya and Max, have their own languages in which people write the business logic, the concrete tools that compose the CAD system. Enterprise software, again, is typically Java-land, but C# is also popular, and most importantly, everything but C++. Now it seems that people don't want to write business logic in C++. And again, I should note that all of these examples do feature a certain core written in C++ and sometimes in C, which is the fast part. For the game engine, the browser itself is written in C++, for example, and the browser runs your websites. Or the underlying web server logic beneath your web server. Node.js, for example, runs V8, Google's V8 engine, which is written in C++. Now, these pieces of software do feature core written in C++ or C, which is responsible for the fast things, the things we want to do fast, but the actual business logic in these pieces of software is not written in C++. And this is the state of the world. And some people might say, okay, this is the state of the world, what's the problem with this? So, let's see some problems. First of all, the code is slower. And people solve it by throwing enormous amounts of hardware to do it, to help it. And they write JIT compilers for languages like JavaScript and Lua too. But even in JIT compiled languages, the norm is typically 3 to 5 times slower than a C++ counterpart written program. And yeah, of course, there are edge cases in which a JavaScript program can be faster than a C++, naively written C++ program. But of course, there are other edge cases in which a C++ program can be tens of times faster than a naively written JavaScript program. And I do say naively because if you make the effort, you can always outperform JavaScript, even if it's JIT compiled. There's also another thing. If you combine C++ and another language, or C and another language, you need to have a binding layer. And the binding layer is a piece of software, piece of code, often of significant size, which takes care to manage the communication between the two languages. And this significantly sized piece of code is more complexity to our code base, more place to find bugs, more things to support. It's unpleasant to do it. And even with the best of intentions, when you have a language like C++ and another language running together, it's not practical to expose every single functionality through the binding layer. Small operations like, for example, I don't know, vector addition, matrix multiplication, usually end up being written in both worlds. And that leads to duplicated code, and duplicated code, of course, leads to duplicated bugs. And then we might ask ourselves, why don't people use C++? And there are some reasons. First of all, build times. Typically, when you write software in JavaScript or in Ruby, you run it and it magically just starts. There's a lot of effort put into making programs like JavaScript engines and Ruby engines do so well in terms of performance, but C++ has to be compiled because there's a lot of stuff going on behind C++ compilation, and it takes a lot of time. But as we heard in our previous talks, we have a lot of things to do for it. The previous talk was entirely focused on build time optimizations. The one before that mentioned modules, and modules are, well, in some cases, really helpful in optimizing build times. But when we talk about hot swap, this is not usually the problem. So if you want hot swap, this is basically running your program and then swapping a piece of code that is part of your program as it runs without having to restart it and basically try to go to the same state that you want to go, just you swap the piece of software and it runs from there. This is really easy in languages like in the languages I just mentioned. But the thing is that C++ has had in C2 hot swap for a long time now. It's not really popular, but it's getting more and more popular. So this is about to get fixed. And I'm not going to focus on this, but you can find me and ask me about it. And hot swap is really, really simple to do in C++ nowadays. Then there's testing. The cool part about languages like JavaScript or Ruby or Python and C# is that they have reflection. And because of reflection, you can write tests which analyze the code, analyze the structure of the business logic, the domain structure, and generate appropriate tests in order to do this, to test it most thoroughly. For example, property-based testing and fuzzing do precisely this. But again, nowadays, Clang plugins are getting more and more popular, and there are lots of, at least jabs here and there, to get you proper fuzzing in C++ and property-based testing as well. And I think that in the very near future, we will see very powerful fuzzers and very powerful code analyzers which generate tests based on libclang. So there's one thing, though, that's actually not that much in development as the others, not that much in focus when we talk about C++ and business logic. And that's OOP, object-oriented programming. And that includes within itself dynamic polymorphism. Now, dynamic polymorphism doesn't necessarily have to be a part of object-oriented programming. The strict definition of object-oriented programming just has some objects which have functionality and data within them. But it really has come to mean it. Now, we will very, very rarely see someone talking about object-oriented programming without also meaning dynamic polymorphism within it. So I'm going to include dynamic polymorphism when I talk about object-oriented programming. Now, object-oriented programming has had a lot of criticisms, even talks on certain conferences about how object-oriented programming is dead, how you shouldn't do it, how bad it is. And all of the criticisms can be grouped into this phrase. You want a banana, but with it you also get the gorilla and the entire jungle. So some criticisms, for example, say that it dangerously couples the data and the functionality. And this is really object-oriented programming. The data and the functionality reside in the same part. And functional programming is on the opposite end of the spectrum, which says functionality and data are never coupled. You have functions which know how to work on certain patterns of data, and then you execute them. Whereas in object, functions and data reside in the same place. Also, another criticism is that it's not reusable. Back in the early days, in the 90s, when object-oriented programming was all the rage, people were saying, okay, so with object-oriented programming, this is so cool, you're going to write a simple module and component and then reuse it a billion times in every piece of software you write. And as Delphi actually showed us, this doesn't actually work. So this promise of object-oriented programming wasn't kept. It's not as reusable as advertised. Anyone here coded in Delphi? Yeah, I pity you. Then another criticism is that it's slow. And this is typically about dynamic polymorphism. And dynamic polymorphism has to be slow. It has to have a certain indirections when calling functions, because it's, as opposed to static polymorphism, which is all the rage in current C++ when you have templates and better ways to construct your code at compile time so it does the best possible thing. Dynamic polymorphism doesn't know about the types. It can't know about the types, so it has to do some code as the program is running in order to execute the appropriate code, I guess, the appropriate functions. So because of this, many C++ programmers have forgotten, or I don't know, perhaps deliberately chosen to forget that C++ is, among other things, an object-oriented programming language. And in defense, I can say this. Many of those criticisms target concrete implementations of object-oriented programming. And I'm looking at you, Java. Some implementations of object-oriented programming are just lacking, just don't allow you to do whatever you want to do. And many of those criticisms are targeted towards misuse of OOP. If every single function of your code is a virtual function, it will be slow, because every single function call will lead to an indirection and a jump, and a call, I mean, not even a jump. Then your program will be slow, and if someone sees that, he's gonna say, oh my God, this is so terrible, therefore object-oriented programming is terrible. Sometimes people even say, therefore C++ is terrible because it allowed me to do something like this. And C++ does allow you to shoot yourself in the foot and blow your whole leg off. So, and that's why we as C++ programmers have heard it many times, C++ is terrible. They've seen some horrible misuse of C++, and I don't know, transferred their hatred of this misuse towards the language itself or the technique itself. And of course, some are about misconceptions of OP. Some people just don't understand what object-oriented programming gives you and write their program so that every function is virtual because they don't understand what the power and what the point of virtual function is. And most importantly, though, the thing that all criticisms miss is that software is written by human beings, so far, until we have the blockchain, artificial intelligence, VR, buzzword thing that's going to write software for us. We still are the ones writing software. And human beings are evolved in a world of objects. Our whole brains are wired so we want to think of objects. And because the real world is, at least according to our brains, composed of objects. Even if it's not necessarily true. For example, in biology, we have these whole trees of species composed of classes and subclasses and kingdoms and whatnot. Whereas if you're into biology, you would know that this is not necessarily correct. Species are not distinct. They're not discrete. They're, at least in terms of time and sometimes in terms of space too, a species is something quite analytic, I guess. It's not a single thing. And if you're into physics, you'd know, for example, that elementary particles behave like waves and like particles at times. And certain elementary particles, like say quarks, don't even make sense when you take one of them. There is no such thing as a single quark. But the thing is that people, in order to produce these theories, in order to evolve, not evolve, but I guess to make biology and physics better, they have devised models which are based on objects which help human beings actually reason about those models, put forward theories. So the same thing goes for code. People are inclined to think in terms of objects. If you have an object, you know, okay, this is this has this data in it, this does these things. You can reason about it when your requirements change, you know, you have your model in your head, which is easy to have because it's composed of objects, and you know what to change and what to do. This is my proposition. Of course, you're free to disagree, but in my head, object-oriented programming should be defended mainly because of this. Human beings think in terms of objects. And come to think of it, every language that I listed before, the languages which actually thrive in business logic-dominated fields where you have complex relationships between different, well, I won't say objects, but parts of your code, those languages are almost all object-oriented ones. Yeah, we all love Haskell, but how many people actually write Haskell professionally? Quite a few. Quite the opposite. Quite a little. The most software in the world is, I guess, written in Java or C# or JavaScript with objects. Check it out. I think it's true. So right now I'm going to list some powerful object-oriented programming features which exist in other languages as a given, and basically think of how we can do this in C++. So we're not afraid of using object-oriented programming in C++. And this is a very simple example. It's in JavaScript, and it's something that you'll see in every single textbook as dynamic polymorphism with object-oriented programming 101. Now in JavaScript we have classes nowadays, but they're basically syntax sugar for functions. So the second part where you see function, you can just think of it as class if you are not familiar with JavaScript. So we have a function which can take a single object, and as long as it has a draw method, it will work. So we have circle and square. We can call a function with circle and square, and they will draw themselves appropriately. And this is another example that you will see in every single C++ textbook when you say virtual functions, and this is the first example you see. This does the same thing. You have a function which takes a shape, because C++ is a strongly typed language. So it takes a shape, and as long as something derives from shape and implements the draw function, this will work. But the problem is this. In the JavaScript example, we had a function which takes just about anything, and as long as it can be drawn, it draws it. So what if our colleagues, or what if another company has written this great shape, which does draw itself marvelously, but it's not derived from our shape? Then suddenly we cannot use our function with it. We cannot just change their entire library. Oh, sometimes we can and sometimes we do, but typically we write wrappers or something like this and add additional complexity to our software. And the thing is that object-oriented programming doesn't necessarily mean modern C++, but since modern C++ is a very powerful language, we can do something about it in this case. And in this particular case, what does help are the so-called polymorphic type erasure wrappers. Now this is Boost Type Erasure, which is a somewhat ancient library. I think it was written in the 90s even. It was one of the first Boost libraries. But modern libraries like that feature the type erasure wrapping is Dino, Poly, which is from Facebook, and Boost T, and T here means type erasure, and Boost is in square brackets because this is not part of Boost yet, but this is supposed to be the next generation of type erasure library in Boost. But what do they do? Basically, we can have code like this. And all of these libraries, really all of them, can be summed by this macro here, library magic. What library magic does is basically creates a type which can accept any type which has the draw function. So now we can write a function which accepts a shape. Then we can have classes which have the draw function, not necessarily deriving from any common ancestor. And this will basically work. And for example, imagine that you want to do something with size. You want to write a function which takes dynamically objects which have size. For example, std vector or std list or std map, they all have size, right? But they don't have a common parent. So you cannot use them in a dynamic polymorphism. And this helps you. You can have a dynamic type erasure wrapper which wraps them and has size, and it basically works. So how does this particular thing work? Here's a very simple implementation. We can have our draw function defined like this, and this is basically the expansion of the library magic macro. So you can have a function which, the std function, which implements draw, and then in our template constructor, we can just bind the type we constructed it with to this function, to this type's member function draw, and the pointer to this type, so it gets called. So basically, if the macro expanded to this, the previous code, this one over here, would work, would do whatever we wanted to do. But in this particular case, you might say std function is pretty slow, it might allocate, it requires us to include whatever, and it's a whole bunch of headers and slow down the compilation. And this particular example is very naive implementation. It just shows what you can do with C++. But just for the hell of it, why don't we try to optimize it? Now in this case, we have a pointer to a function, which is called draw, and we cannot just have it as a member which the person calls, so we have a wrapper function. So the macro will expand to this wrapper function, which calls the appropriate function pointer. And then in our constructor, the class will store a pointer to the original object, and then create this anonymous lambda, the anonymous function, this lambda, which captures nothing from the external world. And if it captures nothing, it's basically equivalent to a free function. So we can set it to this pointer. In this case, our object will still work. We have a better, we have a single hop. So this is basically shouldn't be, and if it's slower than virtual functions, at least in a 64-bit compiler, then your compiler is bad. This should be about as fast as virtual functions. And we can do even more. We can make it faster. We can implement something called the small object optimization. You know how strings have the small string optimization? So basically, they have a buffer, and if the string is shorter than whatever characters, it can be stored in the stack alongside the object. And some libraries, for example, Dino and BoostE, have the small object optimization. So if you have a wrapper like this, it can copy, if it's allowed, of course, and store the object on the stack, and then this virtual function call is actually faster because it doesn't have the dispointer transfer. Or the dispointer, it does have the dispointer transfer, but the dispointer is presumably in our cache. So we can do better than virtual functions with polymorphic type erasure wrappers in certain cases. There's another example. And this is a continuation of our JavaScript example. What if we do have this great library with shapes, and we draw them freely, and we're very happy, but now we want to have areas of those shapes. And the library, sadly, doesn't have areas. It only draws shapes. So in JavaScript, we can do this. We can extend the existing objects with methods, and if we extend every single type that we want to use with area, it will work. We can have a square, we can call its area, and this will work. The thing is that in C++, in order to do this, we just can't, can we? What we can do is edit the existing hierarchy and add the appropriate area method. But first of all, that's not necessarily possible. As I said, it might be a library whose source we don't actually change. And also, it will lead to a tremendous recompilation because our central object, the shape, we will have to change it and every single shape around. But we might want to use this just in a single source file with just a couple of shapes, not necessarily every single shape ever. And JavaScript allows us to do what we want, to extend the objects appropriately. And C++ does so too. There are libraries, and the not Boost type erasure library, the future of type erasure in Boost, and the open method library, or YOM2, allow us to do this. These things are called open methods, and they are distinct from unified call syntax because unified call syntax didn't deal with polymorphism, with dynamic polymorphism. It was just a syntactic sugar to find functions which are called as object dot function and try to compile it as function where the first argument is the object. And this is code which compiles with YOM2 without the inclusion of the headers, of course. And what it does is basically you have a declare method. You say area is my new method. You have a define method. You define the area for a given shape and for all the shapes you want it to. And then you call it in your function. But sadly, I did mention unified call syntax. C++ does not have unified call syntax and probably never will, thanks committee. But we have to write such code by calling a function where the first argument is the this or self or whatever you might want to call it. So instead of pointer arrow area, we need to write code like area and then pointer as the first argument. But this works. This allows us to basically to extend existing classes with polymorphic functions, as long as we call them the way that those functions are supposed to be called. And how does this work? Here's basically a very naive implementation of this. We might have this area function, which is another function. We define a function pointer, which is supposed to be the area function. Then we have the function getter, which, as you can see the implementation below, if the shape is the appropriate type, by using runtime type information, if we can cast it to the appropriate type, we return the required function. This is what the macros expand, basically. The macros expand to this. This is not code that you can just write down. The macros will expand to this concrete implementation that, for example, works for square. So if the object is a square, it returns the appropriate function, otherwise it returns null. And then we can have a registry of such functions. And then in our actual area implementation, we can loop through the registry and see whether the current object which is passed there matches. Now this is very simple to understand, but of course it's terrible because every single polymorphic call like this, we'll have to loop through the entire registry. So we can do better than this. Sure. The thing is that this is very simple to understand. And at the end, of course, if it doesn't match with any of the functions, it might throw a runtime error. We can actually optimize it using, again, more stuff from the runtime type information in C++. We can use type index. And type index is basically something that is implementation defined, but all of our type informations have it. And the thing is that even though it's implementation defined, unordered unordered map and unordered set, unordered containers can actually be, this can be a key in an unordered container. So we can create an unordered map with our area function, and then we can register the function in our registry, which is now an unordered map. And then in the call, we just need to find it in the map, which is optimistically 01. This is, and I grant you, this is a bit slower than a normal virtual function, but it's much more powerful. So again, it's some way of sacrificing, well, a tiny bit of performance for great flexibility. And you know what this language is? Anyone? It's Perl, yeah. Perl is a read-only language, but it's a write-only language, but now we're going to read some Perl. And this Perl 6. Perl 6 has multi-argument pattern matching. Perl has pattern matching. So this code here might look like function overloads, but the thing is that Perl is duck-typed. It doesn't compile. So the, oops, I haven't that highlight here. At the very bottom, you can see that we can get a random shape and then call collide, and then our collision detection library will work no matter what shapes there are in the world. And again, you can do it with function overloads, but then it will be static polymorphism. You will have to know what shapes you pass to the function beforehand. Whereas right now, you can have just a list of unassuming shapes, of type erased shapes, and this will work. So Perl helps us do this. And I don't know if you noticed, but in our previous example, we did something like a virtual table. This unordered map, which we associated with a given function, you can think of it as a virtual table. But the key difference here was that the virtual table was not part of the object, but it was part of the function. So continuing with this idea that we can set the virtual table to be part of the function and not the object, and this language right here has this built-in nim. So we can continue. OK, so first of all, let's try to do it in vanilla C++. I'm sorry, I just went ahead of myself. I was so excited. So in vanilla C++, in order to have this thing, to have a virtual function which is virtual by several of its arguments, you cannot just do it in C++. The virtual table is part of the object, so you have to have this jump collide. So you have this implementation of collide, and then concrete implementations for every possible type which can collide. And then in the classes derived from the basic shape, you override the collide function, so it can call itself with the strongly typed argument, so it can make the dispatch appropriately. So basically, this leads to, if you want a function to be virtual by 2 arguments, you need 2 virtual calls in C++. If you want it to be virtual for 3 arguments, it will lead to 3 virtual calls, but note that this has an exponential growth of the code, because then we will have to make the power of 3 times overloads of this function in order to make it work appropriately for the first and then for the second part. And another thing is that if we add a new shape to our hierarchy, we need to change the base class too in order to add it to this whole list. And again, this is very unpleasant, but it's easily solved if we do what we did in our previous example, and that is add the virtual table to the function and not the object. So this is multiple dispatch. And again, Poly, the Facebook's library, and Yom2 allow you to do some way of multiple dispatch. So basically, this is, again, Yom2 code, which, again, using declare function and define function, define method, declare method, and define method, you can basically note the virtual part of the arguments in the macros. They work like advertised. And how do we make this work? Again, we just reuse the entirety of our previous examples code. But in this time, we cannot have a key to the unordered map, which is a single type index. We have to have this thing called a type hash. Of course, if you have for 2 or 3 classes, you can have a pair or a triple of size t's. And in order to get this size t, you have to use this thing called hash code. And hash code is again something that runtime type information gives you, and it's a size t associated to the given type, which is guaranteed to be the same for the type no matter where it is. And the rest of the code is basically the same. And here's another example. And this is a game. Let's call it a game. So in this game we have flying creatures, and in this game we have creatures. And creatures in the game can move to certain parts of the game's world. And for simplicity, the game's world, in this case, is composed of the integers. Let's say the positive integers, or I don't know, any integers. So the flying creature has this method called move_to, and it flies to the given target, or it cannot fly to the given target based on can_move_to method. And because it's flying creatures, and flying creatures don't care about obstacles and whatever, it always returns true on can_move_to. And then we have this thing, afraid of evens. And afraid of evens is a thing that returns false if the target is an even number. And in Ruby, and this thing right here is a complete Ruby program which can work on its own. You can just load it in Ruby and it will work. You can create an object. You can extend it with a flying creature. And then you can say it move to 10. It will readily move to 10, of course, because flying creatures don't care. But then you can extend it with your afraid of evens. And what happens here is that the can_move_to method of afraid of evens overrides the existing implementation of the object that we just created. And now we have an object which is composed of move_to from flying creature and can_move_to from afraid of evens, so it won't move to 10. And what do we do in order to get this, I don't know, naively in vanilla C++? I had a whole talk about it, the whole 40-minute talk about starting with this Ruby example and then going through different implementations in C++ in order to get it to work. And one of the final ones is this. This is the interface to component pattern. So in it, you can have components within your object, which are different interfaces, and you need a different interface for every single functionality your object can do. And then when you extend the object with a particular interface, and you need multiple overloads of extend, of course, in order to work for your different implementations of those interfaces, you can do this. You can set these interfaces to what they're supposed to do, and then you have this nice code which looks a lot like the Ruby code. You can have an object, you can extend it, you can move to it, and then the interfaces will override themselves appropriately. But what we do have in modern C++ is this library, and this is a shameless self-plug because I wrote this library. But again, much like the Ruby example, save for the headers, save for the includes, this is an entirely self-contained program. You can just add the appropriate includes and it will work. And I cheated a bit because the font is smaller, but this is the entire C++ program. In it, you can define messages, and messages are basically your interface, the components of your interface, and they are not bound to objects or implementations by any way. This is just the interface. Then you can have a creature to class which implements the parts of this interface, and note that it doesn't derive from anything. And in order to basically refer to your owning object, use this macro dmthis, which is highlighted over there. Then you can define the mixin, and yeah, I'm using the word mixin here. So dynamics means dynamic mixins. In C++, what we call mixins are static components which, through CRTP, can be used to compose objects. In this case, because this is runtime, they're called dynamic mixins. And in the Ruby example, this is what's called Ruby mixins. So anyway, that's the mixin explanation over here. So we can define the mixin and say which parts of the interface, which existing interface pieces it implements. Then we can define another mixin, and it say which pieces of interface it implements. In this case, we say that this one implements the can_move_to message with a higher priority, which means that if it both end up in the same object, this one will override the existing implementation. And again, we have this simple code which is basically the same. We can create an object, add flying creature to it, move to 10, add afraid of events, move to 10, it won't move to 10 because we've overridden only a single method in it. And now I won't give you the demo because we're out of time, but if you want, you can come to me later and I'll show you the demo. But imagine it's the best demo you've ever seen in your life. It just convinces you that object-oriented programming is the way to go for everything, and every single function should be virtual ever. So how does dynamics work? We have, again, a registry of message information. So this is the pieces of interface we use. And we can register each one globally, like this. We can just create an anonymous function and call it as in the same line that it's created, and that's how we fill the registry. Then we can have this the same way of using lambdas which don't capture anything because they're equivalent to free functions, and free functions are guaranteed to be equivalent to void star. We can have a void star function which just returns the color according to the mixin it's given. Then we have this function move to which needs to have the implementation, but we won't do it right now because first we have to create the mixin registry, and it's registered basically in the same way, but in the macro expansion, for example, of the move to mixin, we can resize its member functions to the whole list of possible interfaces, and then to the ID, to the appropriate ID, we set the appropriate color. So now when we call move to, it will know where to find the implementation. And then we have this function which returns the info, which is an overload. So because of ADL, if we call this overload in a template function where this overload is seen, it will be called appropriately. So now we have the object. The object has some mixins, which is pretty simple, just a list of types, just a list of pointers, and they're void because the mixin can be basically anything. And it has the virtual table, and the virtual table has the pointer to a mixin and the pointer to an implementation. And when we add a mixin in it, we get the info. This is a template function. This will work. We get the info, and then for every function which the info implements, we override our existing implementation inside. Now, this is oversimplified. It's not exactly what the library does, but it's a good idea of how it does it. And then now we can implement the move to function. Oops. The move to function is very simple then. We get the object, get its virtual table, get the appropriate index of the function that we need to call. We reinterpret cast the function to whatever we want it to be, because this is a macro expansion. We know what to cast the function to. And then we can call the caller with the appropriate mixin pointer, and it will just work. This patch works magically. So the whole point of this is to show some, definitely not all. I missed a lot of modern C++ developments which help you do better and better object-oriented programming, but to show you some implementations and give an example of how they can be done. So you can start thinking in using more C++, even in business logic. And sure, go ahead and explore more and see that modern C++ allows you to be as expressive and as performant and more performant than, for example, Ruby or other languages. Basically what John said. Modern C++ is here, the beast is back, and thank you.
Thank you for your talk, and kind of odd question maybe, but have you tried to actually benchmark your examples versus the scripting language that you provided, or versus other languages that use that?
Right, not all examples. Dynamics is extensively benchmarked, and it, in most cases, is about as fast as a virtual function. So. And if you benchmark virtual functions with languages like, I don't know, Ruby or Python, they're vastly superior. And if you benchmark it against JIT-compiled languages like JavaScript and Lua, in certain cases, JavaScript and Lua can be better if it's very friendly for JIT, but that's not the majority of cases. The majority of cases, if you want to use dynamic polymorphism at all, then you have some kind of a heterogeneous list of objects. So what JIT will help you if you had a list of all objects are the same type, and JIT will help you very much there, and it will make it much faster than virtual functions. In most cases, this is not the case, so they're comparable to perform in terms of performance.
Yep. Thank you.
Anyone else?
So it is always said to see a lot of macros in C++ code, especially when we say that C++ code is modern. So I wonder, do you see these macros as a language extension in the future, or?
This will very likely be the case, yeah. And given how much libclang and libclang tooling is being developed nowadays, most of these macros will probably disappear. And we will have some kind of some ways to do it with the language itself. Especially if you have like the promised land of static polymorphism, where you can compose and at least analyze types with compile time C++ code, then most of these macros will be pointless in this case. But the thing is that, as you see, they expand to pretty complex structures. They need to generate functions, objects, they need to fill lists. It's not easy to get rid of them right now.
Okay, thank you.
Anyone else? So thank you.
Thank you.